Hey everybody, Dr. White here with the beginning of a series of applications of integration. We're going to look now at finding the area between two or more curves in a plane instead of just like the signed area underneath a curve down to the x-axis. Let's complexify this a little bit. So check out this figure over here where we've got two functions, y equals f of x, y equals g of x. And g of x is always less than or equal to f of x for all of the x's in the closed interval from a to b, all of the x's from here to here. So how might we find that area? Well, we could use the idea of approximation with rectangle areas. And so the book does it a little more formally. Usually the instructors are kind of invited to give you the less formal approach on the side when they talk to you. So I'm going to give you this less formal approach. I'm not going to do a bunch of stuff with Riemann sums. I'm just going to say, what if you got like a whole bunch of like infinitely thin rectangles, okay? Like here's one over an arbitrary value of x between a and b. Here's our infinitely thin rectangle up here. Its thickness is dx, an infinitely small change from x to x plus dx, maybe. And the height of that rectangle would be the y-coordinate at the top minus the y-coordinate at the bottom. So the y-coordinate at the top is f of x, the y-coordinate at the bottom is g of x, so the height is the difference between the two. So what would be the area of this infinitely thin rectangle? Well, being a rectangle, I'd say height times width. So the little area, little infinitely small area, so I call it dA, is f of x minus g of x times dx. So how would you get the area of that entire region? Well, you would add up the little infinitely small areas of all of those infinitely thin rectangles, starting from the x that's right over A, all the way up to the x that's right at B. And so you would get the definite integral that you see right there. Okay. Now, I should point out that the region that you're looking at here, where we set up that nice integral, it's what we call vertically simple. The book is a little bit hazy in its definition of what simple means for a region, but the idea they want you to get, I think, is that a region is vertically simple if there is always one particular function that's on the top that has the higher y-coordinate and another function that's on the bottom that has a lower y-coordinate, okay? And so the idea is that the formula for the top y and the formula for the bottom y aren't going to change on you anywhere over that region from A to B. On the other hand, if you have a setup like this, okay, so imagine this region here stuck together with this region here. That total region is not vertically simple. And the reason is the F curve is bigger than the G curve only some of the time, from X is A to X is C. At C, they're equal, the curves, their heights are equal, so the curves cross. And then from C to B, it's the G curve that's bigger than the F curve. Now, it's always going to be true that the area of your region is the sum of the areas of little thin rectangles, and that you can get their rectangles using y-coordinate at the top minus y-coordinate at the bottom times dx, as long as you can find y at the top in terms of x and y in the bottom in terms of x. And you can do that always. It's just that the formulas for the y top and the y bottom, they're going to change around the value x equals c, okay? So like to get this part of it all, you're going to integrate from a to c, f minus g dx because f of x would be the formula for y top, and g of x would be the formula for the bottom y coordinate. And then integrate from c to b g of x minus f of x to account for the fact that g's higher now. Now, if you wanted to write it out in terms of f and g all with just one integral, you could. You could say that the area of that whole region is the integral from a to b of the absolute value of f of x minus g of x, so that you always get, a positive number for your height. So you're counting all your area as positive like you want. But that doesn't save you when you're computing from the necessity of breaking up into these two integrals. So you're not going to see a formula like this in the book, but when you look on the web and study calculus from other points of view, you'll often see them cite this formula as a way of getting the area between two curves f and g. Let's just try something else after I have a sip of coffee. Now let's find the area of the region enclosed by the graphs of these two functions. F of x is x squared plus 2, and g of x is 2x plus 5. Now, I just want to let you know that when you get a problem like this that's all in words, and you're wondering, like, gee, what does that region look like? You could actually go to the internet these days and use very powerful systems to make it do the graph for you. I know you could do that. In fact, I'm just going to do it myself because I know you can do it, and I just want to be along with you while you do these things from time to time. So I'm just going to head to the internet somewhere. How about up here, and I'll Google Wolfram Alpha computational intelligence machine. All right, and I'm just going to see, like, could this actually tell us the area between y equals x squared plus 2 and y equals whatever that other curve was, 2x plus 5. Okay, let's see if we can figure out what we want. Wow, gee, it did. And so x squared plus 2 is this parabola that you see here that crosses the y-axis at 2. And then here 2x plus 5, or 5 plus 2x as they write it, is that line with slope through that goes through 5 on the y-axis. And they've kind of shaded in the area that you're asking to look at. And they even rather nicely went and found it exactly for you. It's 10 2/3. So I know you can do that, and I suppose when you're practicing, it's fine to check your work that way, just like you would go to the back of the book, and look at the answer in the back of the book to check your work on an odd-numbered practice problem. That's totally fine, but don't let it go so far that you never figure it all out for yourself. Let's head back to our notes and figure this out kind of from the ground up. You could graph a parabola pretty easy. You can tell that it goes through the y-axis at 2, and it has a parabola shape. And you can graph the line y equals 2x plus 5. Go to 5 on the y-axis and then have it, move up with positive slope. And so you can tell that these two curves cross somewhere and somewhere else. And you know that if you're going to find the area, you're going to need the formula for y at the top. And from the graph, you can tell that's always going to be 2x plus 5. You're going to need y at the bottom, but the parabola is always underneath in this region, so that'll be an x squared plus 2. But you're going to need the lower bound and the upper bound, and that's the place where the two curves actually meet. Here and here, we need their x coordinates. So make sure you can figure how to find them. Two graphs are going to meet when they have the same y coordinate for the same x coordinate. So like what you could do is say, well, when is the 2x plus 5 y coordinate going to be equal to the x squared plus 2 y coordinate? And you solve that equation and you come with a little quadratic that you can factor. And since the product of those two factors is 0, then either one factor or the other has to be 0. So the x either has to be 3 or -1. And so you can tell that the lower here is a -1 and the upper here is a 3, just like we saw on Wolfram alpha. And so you could set up your integral. And so here's your y top and here's your y bottom. Notice that although those are y coordinates in our picturing of the skinny rectangle, they've got to be expressed in terms of x because the x is the variable of integration when you're using these little vertical skinny rectangles. And so you simplify as much as you can, you take an antiderivative, and by whatever techniques you've learned so far, you evaluate between -1 and 3, you play around with it, and you do indeed get a 10 2/3 like Wolfram alpha did. So I wish, life was always so easy, but it's not. Sometimes you have to think carefully about the nature of your region graphically and carefully set up the integrals that would correspond to the area between the curves you're interested in. I've modified something here from the book in the exercises somewhere. You've got this line here, and it goes through 4 on the x-axis, but you're not told its slope. So you just think of this equation as y equals g of x. And you've got this curve y equals f of x, and they don't tell you anything else about f except that it apparently crosses the x-axis at 8 and at 13, and it's above and it's below in the regions indicated. And you've also got the x-axis itself. And the shaded region is bounded by these three curves: the x-axis, the falling line, the g of x, and also the f of x curve. And we want to find the area of that shaded region. How would you do it thinking in terms of integrating across the x's, y top minus y bottom? Well, from 0 to 4, the y top is the f of x. From 0 to 4, the y bottom is the g of x. So you're going to need that integral. From 4 to 8, things change. The y top is f of x. The y bottom is the x-axis, where the y coordinate is 0. So you can see this. And then from 8 to 13, the y top is that x-axis where the y coordinate is 0, and the y bottom is the f of x. So 0 minus f of x, and f of x is negative there, minus f of x will turn positive, giving you a positive area here for that final piece. So you had to break up your task here into 3 definite integrals. The formulas for y top and y bottom changed on you over the x region you're interested in. Now, sometimes you'll face situations where if you think of it in terms of vertical strips, you've got a problem that there aren't even really top and bottom functions for you. Like, what if I wanted to find this region here? I'm just going to make it with my mouse from here to up to here, over to here, down to here, then back. So that kind of little thing here that I'm kind of waving inside. If you thought of it in terms of, vertical rectangles, well, some of the rectangles would have a top at B and a bottom at A. A lot of them would. And some of them would have a top at B and a bottom at this other curve down here. And the problem is that other curve isn't even the graph of a function of x, because it violates the vertical line test, And so that's going to be really hard to work with, algebraically. And it's even worse over here. Some of the rectangles would be bounded by one y coordinate belonging to the left-hand curve and another y coordinate belonging to the left-hand curve. Yuck. So let's think in terms, instead of vertical tiny rectangles, think about horizontal tiny rectangles. So now, from the y equals a to the y equals b level, consider an arbitrary y level, okay? Right here. And so that corresponds to a skinny little horizontal rectangle at level y whose thickness is dy, okay? Now, we're going to need to multiply the length of that thing by the thickness to get the area. What would be the length? Now, we need a positive number for the length. So what we need to do is go to the right-hand x-coordinate and the left-hand x-coordinate and subtract right-hand minus left-hand. Bigger x-coordinate minus smaller x-coordinate. That'll be the length. And so our area formula could be summing up from y is a to y is b, the little areas of these little skinny horizontal rectangles. Just make sure when you implement this, and we'll have a chance, we'll do some examples. When you implement this, x right is going to have to be expressed in terms of y, the y level. And x left is going to have to be expressed in terms of the y level, because now the variable of integration is y. So like here's an example. Say you've got this curve x is y cubed minus 26y plus 10. And this curve x is 40 minus 6y squared minus y cubed. The graphs of these curves are shown below, but they're not telling you like which one is which. Like this one here, is it the graph of x is f of y, or is it the graph of x is g of y? They are telling you some things, though, that are nice. They're telling you that the f and g graphs, they intersect when y is 3, when y is minus 1, and when y is minus 5. So that's nice. And let's say what we want to do is we want to find the area between the two curves. So it's this top little banana little shape plus this bottom little oval shape, okay? That's the region whose area we want to find. Clearly, we're going to need to break this into two integrals. We're going to have to go y from -5 to -1. And we're going to have to do, an x right minus an x left at each of those levels. And then we're going to have to go y from -1 to 3. And we'll have to, again, do an x right minus an x left. It's just that what's right and left is going to change on us. Now, before we can really get that set up, we need to figure out, like, which is which. So here's one way to figure that out. Just kind of like think about one of these equations, and I'll just think about this one here. And I think, like, all right, if I were to like let y get really big, like be a really big positive number, then minus y cubed would be a huge negative number compared to this stuff here, because cubing is much more powerful than squaring when y is big. And so the result is that the x ought to be negative when y is a big positive number. So at big positive numbers, so like where I'm waving my mouse here way high on the y-axis, I ought to see negative x's. My curve ought to be over in this quadrant here, the fourth quadrant, where x is negative and y is positive. Another thing is that when y is a big negative number, then minus y cubed would be a big positive number, much bigger than any negative that you would get out of this. And so the result is x would be positive. And so I think, like, which of these two curves is negative x when you're high and positive x when you're low? And that would be this curve here. And then going down, and then, oh, it's the f, okay? So the f is the 40 minus the 6 squared minus y cubed. So the g is this other one here, okay? So that reasoning is sort of briefly talked about here if you're examining the notes later. So once you've figured that out, you can tell what's going to be your x right and your x left all the time. From y is -5 to -1, it's the g that's the right and the f that's the left. Ta-da. But from -3, from y is -1 to 3, it's the f that's the x right and the g that is the x left. And so writing in what things are, you've got this complicated stuff that would not be hard to simplify and to, integrate and if you needed simplify to some simple solution, but I won't be bothered. One more example. Let's say you had to find the area bounded by the following three lines. Line A has equation x plus y is 4. Line B is x minus y is 0. And line C is y plus 3x is 4. Okay, you should definitely look at the region before you start any other work. So you need to graph those three lines, and for most of us, graphing lines is easiest when we write it as y in terms of x. So that's my first move here. I'm just going to solve for y for each of those three equations. Feel free to stop the screencast anytime you want to just do the calculations yourself and see if you're coming out like I am. And then once you've got those three equations, you want to graph each one of them. And so when I graphed line A, which is this one, I ended up with this thing that starts at 4 and goes down with slope 1 and goes to the x-axis at 4. So there's line A. Line B is the line y equals x, which goes through the origin and has slope 1. So here it is, kind of running diagonally up and to the right. And line C, which is 4 minus 3x, it starts at 4 on the y-axis, and it goes down pretty sharply with a slope of -3. So, here's the line C. And so the region between them is some kind of triangle. And the sad thing is that that region is neither vertically nor horizontally simple. Because if you try vertical strips, you'll see that the formula for top and bottom changes right around this point here. And if you try horizontal strips, the formula for left and right is going to change right around this point here. So your life is not easy no matter which choice you make, horizontal or vertical strips. For purposes of illustration, I'm going to try both types of strip just to, get us some more practice in setting stuff up. So for any setup, whether you do horizontal or vertical strips, you want to know as much about the corners of your region as you possibly can. So like I know about this corner here, but I'd like to know about this corner here and this corner here, okay? So I could look at like where do line B and line C intersect? Line B and line C, they're intersecting right here. Let's see if we can get that point. And so we take the line B and the line C curves and we set the y coordinates equal and find what x that happens at. Turns out it happens when x is 1. And so then we got to find like what is the y coordinate, and we say, well, you know what? Y is always x because we got to be on line B. So y would also be 1. And so that point right here is 1, 1 all along. And similarly, this other point is where line A and line B intersect. Same idea, take the equation, set the y coordinates equal, get the x, get the y off of that. And it turns out the coordinates at that point are 2, 2. And so you can add to your drawing. And so I'm not shading in the region here, but it's the one that's bounded by the lines connecting the points 0, 4, 1, 1, 2, 2 back to 0, 4. And I have my choice. I could do vertical or horizontal strips. Let me start by doing vertical strips. And so I think to myself, okay, x-axis from 0 to 2, because the lowest x for this region is a 0, and the highest x for this region occurs at that corner 2. And then I'm just drawing 0 to 2 on the real number line and drawing my region over it. And I'm thinking, there's going to be a change when x is 1. Between 0 and 1, when I choose an arbitrary x, my little vertical strip is going to have line A for the top and line C for the bottom. But between 1 and 2, my little vertical strip is going to have line A for the top and line B for the bottom. And so when I do the area, I've got to do the integral from 0 to 1, line A minus line C, y coordinates, it's expressed in terms of x, plus integral from 1 to 2, line A minus line B, y coordinates expressed in terms of x. And so I could do that integral out. If it was horizontal strips, then I should think about the y-axis in relation to the region that I want. And I think, like, what would happen for arbitrary y levels? Well, I know there would be a change at y is 2, because that's that 0.22 at this corner here. And so I think, like, what's it like for y's that are just from 1 to 2, y 1 to 2? Oh, when we look at our region, the lowest y coordinate is 1. The highest y coordinate is 4. That's why on this y-axis, I've marked out everything from 1 to 4. Okay. Well, anyway, from 1 to 2, if I take an arbitrary y, then in that horizontal strip, the length of it is the rightmost x given by line B minus the leftmost x given by line C. Okay? And those right and leftmost, they need to be given in terms of y. So when I look at, for example, line B, instead of like thinking of it as y equals x, I'll think of it as x is y. My rightmost x is going to be y. When I think about line C to get that leftmost x, instead of thinking about it like this, I'll solve for x to get x is 4/3 minus 1/3 y. That'll be my formula for x left, as long as I'm between 1 and 2. And similarly, when you're working at y's from 2 to 4, you're going to need to use the line A to get your rightmost x, but you'll express that as 4 minus y. And so that leads to this other setup. Either sum of integrals would result in the same area if I've not made any algebra mistakes along the way. So that's all I've got for section 6.1. Plenty more practice in WebAssign and odd-numbered problems you can just totally pig out on. But great to do more practice on your own. All right, let me see if I can end the screencast. See you later.